Okay, so now we're recording. All right, and I will share my screen momentarily. Let me tell you what we're going to be doing, and I'll start sharing the screen right now, as a matter of fact. All right, share sound. Yeah, usually, guys, I'm a little bit more organized than this, Florian and Michael, but maybe not so much. Okay, stereo, share sound. Okay, share my desktop. Okay, so there we go. All right, leave that in the way. And we got Nicola and Eliana and me. All right, so what I want to show you is basically you're going to see some really high-end tools because machine learning has become this huge, huge industry. And the use of AI tools in almost every sphere of any sort of life that impacts data is just significant now. And like I said, I know a lot of the tools. I know actually very early versions of the tools. But Nicola's the one who's been actually using it in his sort of musical life. So I asked him to take the next couple of lectures and talk about his engagement with some of these tools. And he's going to give you his typically fun stuff. Remember, the watch was just astounding. Of course, I wiggle my wrist without the watch. But talking with Nicola, it might be good for you to just kind of understand what's going on underneath. I mean, how many of you know about neural nets at all? A little bit? So this may be like really stupid for you, okay? You know about how they sort of configure themselves and things? Oh dear, I'll make it a fast lecture then, okay? What I want to do is talk about, the underlying sort of architecture for a lot of these tools is a neural net, all right? And in fact, they're quite sophisticated. I'm going to show you probably the most basic neural net there is. And I'm going to draw it out. I mean, first of all, just to understand what we're doing, and you'll understand why it's called a neural net. Okay, so let me create a new image. That looks about right. Okay. Oh, that actually isn't right. Okay, file, new image. I want to flip these guys. I want this to be 1,000. I want this to be 700. All right, yeah, I want it to look more like that. Okay, so get rid of this guy. Okay, and maybe I'll save this. Who knows, just for fun, I might put it up on the web. Okay, so we'll say save. And let's go over here to my data sonification class, week 9, and we'll call this net, neural net.pdf. I don't want to save it as a PDF, I want to save it as a JPEG. Okay. All right, so I saved it. All right, so, oh God, there we go. So what is a neural net? Well, there's the first thing that you've got to confront is you're going to present data to something that's then going to transform that data. So the very first thing you have to do is figure out how are you going to encode that data and what is it you're going to try to do. And the very simple sort of thing that I'm going to show you guys is basically a really crude timbre classifier. Okay, I'm going to give it like basically fake FFTs, all right? These FFTs are going to be so fake that they're only going to have 8 total data points. Now, there's actually FFTs like that, Yeah, in fact, here's an interesting story. Because you all know this anyhow, I can tell you interesting stories. Dan Ellis, when he was working here at Columbia, did some work for a company called NEC, which is a big Taiwanese sort of company. And this is back when Napster, do you guys remember Napster? Some of you guys have no idea what it is. That's amazing. Napster's the thing that broke the music industry. It was the online sharing app that people started using to trade sound files back and forth. And that's what then paved the way for Apple iTunes to take place, okay? But for a period, all of a sudden, the bottom fell out of any sales of music because everybody was getting it all for free. It was a golden age. So, yeah. They were coming up with a way of identifying if you had an illegal sound file on your computer. And they discovered they could do it by using 8-bin FFTs. was a very crude look at the sound, but it was enough to determine whether or not this was a piece by Metallica or something like that, all right? Now, here's why that project was doomed to failure. Because NEC imagined that what they would do is at night, their software would come into your computer and scan all the files and then take the data back to NEC. Yeah, that's not going to happen. That's not going to happen. But anyhow, so we're going to look at, basically, very simple, like imagine that there's a slot at 125 hertz, 250 hertz, 512 hertz, 1024, and up to, some ridiculous number. And we're going to give it these fake FFTs, and it's going to tell us, is this a low sound or is this a high sound? Okay. So our initial encoding is just going to be those 8 numbers representing the height of the FFT there. So the way you would do that in a say I'm going to draw it out here. I'll just use a pen. Okay, I'll put one there. Whoa. Oh yeah, that'll work. Cool. I forgot I had an arrowhead going on this. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so those are going to be the numbers that we give it, the FFT numbers. Okay, now what's going to happen with those numbers? Well, we're going to take those numbers and we're going to send them to what we call a hidden layer. Okay, and I'm going to talk about what I mean by sending them to there. Okay, we're going to take another 8 here. Okay, maybe I'll change the color. Maybe I'm going to get too carried away and this is going to be ridiculous. Okay, all right, we'll make this green. Okay, so I'm going to send this here. 2, 3, 4, 5, 6, 7. See, normally I would do this on the whiteboard, but since we don't have well, never mind. Okay, let me turn off the arrowhead, and here's what we're going to do. Okay, isn't this just fascinating, guys? Okay, all right, we're going to say, it's going to take this and it's going to send it here, 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 and here. And I'm not going to do that for the rest of them, but assume that that's what happens, okay? Now, what these are the nodes of the neural net, okay? And then these are the edges or the connections that go from one node to another. And what's going to happen is you're going to get a number in here representing an FFT value. When it goes to this node, it's going to be multiplied by some factor here. It's going to be multiplied by some factor here, multiplied by some factor here, okay? And then the next thing that it does is it sends it, I'm not going to bother putting on the thing, we're going to have another layer here, okay? And it's going to send all these guys out to here, okay? Just assume, okay? Yeah, actually, even when I do it on the whiteboard, I usually give up after a while because this is ridiculous. Okay. All right, so these guys are all going to go, and again, we're going to do that for each one of these to this node also, and they're all going to get multiplied then. So what you wind up with is a set of numbers here that's calculated by these multiplications. And then you're going to wind up with a single number here that's determined by calculating all those multiplications, and you'll get the same thing over here. And then finally, you send these out and you get a single number out here. Now, here's the magic of how this neural net works. First of all, it's called a neural net because it's roughly based on a very crude idea of how neurons work, which is basically you have a whole bunch of chemicals at the synapse that go to the next neuron over, and if they exceed a certain threshold, then that neural net will fire. So those numbers that we're weighting and putting in like all these things, those are supposed to be the acetylcholines and stuff like that that are coming in to do this stuff, all right? But they're just numbers. They're just very simple numbers. What happens is we're going to train this to produce a number close to 0 if it has those guys prevalent. And it's going to produce a number close to 100 if it has those guys present. How do you train it? Well, here's the magic. You basically go in and assign random factor values to all of the edges in the network. Then you calculate it, and you'll get a single number out. And if you gave it a low sound, that number is supposed to be close to 0. If it is, you go, okay, cool. Then you go in and you randomly change all of these things and recalculate the network. If the number is closer to 0, you go, oh, cool, we'll use these new numbers. And then you go in and do the same thing, and you repeat this for like 10,000 times. And after repeating it for 10,000 times, you have a set of multiplier weights, they call them, that will then basically, if you send in these guys, it will produce a number close to 0. If you send in these guys, it will produce a number close to, say, 100, okay? And the amazing thing is it works. You know, I think it's kind of like magic, you know? The other thing that's amazing about it is that these, this is a very simple operation. Once you train this network, it's just a simple series of multiplications and additions, and that's trivial for a computer to do. So you can do it in real time very easily. Now, this is a really stupid neural network. A lot of them have recurrent nodes where they've got several hidden layers, and they'll actually feed back up into ones above it and things like that. You know, there's all kinds of what they call different network topologies. It's a big area of active research. There's also all different ways of changing those weight values. You don't necessarily do what I just said, where you just kind of randomly move them. There's different like constructs that you can, mathematical approaches that you can take to kind of creating these weighting values that turn out to be much sharper. So that's where a lot of the research in neural networks is happening right now. And they've found that certain networks are good for certain things. So these tools that Nicola is going to show you relies upon some architecture that they've already kind of proofed and said this is going to work pretty well. Okay? But the cool thing is that I actually implemented this in Msp, and I can show you how it works. The hardest part, I'm not going to show you the code because it's kind of ridiculous. The hardest part is just keeping track of all the numbers, you know? And especially when you start getting into like really huge networks, like if you're looking at an image and you're looking at all the pixels or something like that, you know? There's actually now a lot of work looking at how you automate the creation of a network, you know, and things like that. Anyhow, let me show you then the magical thing. And you'll see that there's also, this is based on, I have to put in the attribution here. When I first did this, I was in a class in 2005, I think. And we had a new graduate student at the time who's working for Google now, as a matter of fact, named Daniel Iglesias. And he was highly recommended. He did his undergraduate work at Princeton. And my colleagues down there said, you know, yeah, he's really good. So we accepted him in our program. And I'm doing my lecture, and the whole time he's back there typing on his computer, you know. I'm thinking, okay, Princeton jackass. I can say that because I went there too. And I said, you know, he's obviously not going to learn anything from me. And, you know, he's probably answering email or something like that. And at the end of class, he comes up and goes, hey, Brad, I really liked your lecture today. Yeah, sure. Okay. He said, but I think I made a better version of it. And the whole time he was recoding my code, and his version is a lot better. So for that reason, I let everybody use laptops in my class whenever they want to. Okay, so anyhow, let me bring this up, and I'll show you how it works, okay? Then we're going to turn it over to Nicola, and we'll take it away from there. And again, you're going to notice this is so old it was written in Java, not even JavaScript, you know, so that's the actual code for it right there, okay? And come on, Max. There we go. All right, there we go. So this is it, okay? Just to show you what's happening here, this is the actual place where the neural net is computed, all right? This is the training system, and then this is going to be how we then test it, okay? These are some tests, okay? The way this works is that Uzi is, oh, those Max MSP guys, it basically sprays out a whole bunch of bangs, like a machine gun, apparently, okay? So when I hit this, it's going to like hit 5,000 bangs. Those bangs are going to line up, so it's going to go bang, 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 bang. And for this one, it's going to say, all right, 111,000, that's low. I want it to go to 0. This one, it gets banged, it'll be 000,111. That's going to be high. I want it to go to 100, okay? So that when this gets completely trained, I'll be able to send it those things, and it should give me a 0 or 100, depending on which thing I do. So let's go ahead and do it. I'll reset it here, and I'll hit this Uzi. Okay, and I discovered I have to hit it several times because I really wanted to learn. Okay, now let's check it. Okay, let's send it a high sound. Zeros in the low parts of the FFT, ones in the high parts. Let's calculate it. Ooh, it's close to 100. Let's send it a low sound. Ones in the low part, zeros in the high parts. Let's calculate it. Ooh, it's close to 0. It learned. Let's try to confuse the poor thing. Okay. Ooh, it's 50. It doesn't know. So now we can say, all right, what if we have a sound that sounds like this? Calculate it. Ooh, it's 8. It says it's a low sound. And in fact, there is a lot more low frequency stuff there. Let's send it some high sound. What's that going to do? Ooh, 84. And you can even kind of use the numbers of the network to determine, like, you know, how sort of like, if we do something like this, for example, what's it going to do? It's 58. It's kind of a high sound, but not really. Okay, we can do something like this to really fake it out. What will it do? Oh, 24, not bad. Okay, so it's still saying that it's basically a low sound. Okay, so that's how this neural net actually works. And again, it's very simple, very, very kind of basic stuff, but it's kind of remarkable that you can now just put in these like weird. I think in my original class we actually set up an FFT real-time thing that did like an 8-bit FFT. It would go and it'd go low sound. It'd go and it'd go high sound. So maybe not that. Anyhow. Okay, any questions about this or anything? I mean, was that too stupid for you guys? Okay, if you probably already know, but if you really want to get into this, the book to read is still Nicola and Rummelhart. They were the guys that first did neural nets. Well, actually, the guy that first did neural nets was Marvin Minsky back in the early 1960s with a thing called perceptrons. And he thought that they had proven that they wouldn't work. But it turns out he was wrong. And they actually have it working now. It's like, well, it's kind of taken over our lives. And, don't be a criminal because it will recognize your face. Things like that. All righty. You ready? Yep. What's this? Yeah. About the neural, yes.
Yeah, does say that encode is audio data, I guess?
Well, in that one, I mean, basically, it's abstract data. Hold on.
Set up the audio here with loopback, but that should be.
Example, what is it? Just kind of like, oh, this is how we can use the neural net on audio data to then maybe tonify some output, or is there something about neural?
Eliana, can you hear us?
No.
If yes, can you raise a thumb?
It's just, it was so
Or
simple,
something.
nothing apparent.
Interesting to like sonify the
Cool,
weights of the
thanks.
network as it learns. Right, like each step that you take to like learn the different output.
Yeah.
It would like eventually converge, and you kind of got this converging sound.
Yeah, well, that's what's interesting, and that's actually one of the things, neural nets are still kind of mysterious, you know, and they don't quite understand a lot about how they work. And there's not a one-to-one mapping, you might think about how the weight shift. I had a very early version of this that I did for a system called X Windows, which is popular on Unix machines back in the early 80s. And it would actually like thicken and color in the branches. And it was kind of weirdly random. You know, you couldn't necessarily tell that this was gonna like, you know, these guys are gonna converge and these guys are gonna converge. It's an interesting idea because sonification might reveal something.
About that convergence.
Yeah.
Maybe.
Yeah, cool. Okay, Nicola's online, right?
Yeah.
Everything's working?
Yeah.
Good. So
Uh,
let's go.
Yeah. So maybe I would just say how like the next classes are organized to like
we
get
got
a frame for
syllabus.
what we are doing.
Yeah.
So the idea with this part of the seminar was to look at different objects which are usually used at the moment in MaxMSP, and to basically like really have a look at how these things works and how they can be used, and I don't know. And so for this class, now we are looking at a bunch of objects programmed by Benjamin Smith from University of Illinois called ML star. Next week, we're going to look at Mubu, a multi-buffer, which is released by IRCAM from Paris. The week after, well, we still have to see it. Then Pierre Tremblay is coming by together with Ted Moore, and they will show Flucomar, which is the sort of class of objects which they have been developing for machine learning in MaxMSP. And the last one is going to be Federico Visi. He is a researcher at the UDK in Berlin, and he developed a bunch of machine learning objects which are specifically geared towards a movement interaction and machine learning with gesture recognition. I should say that sort of what we are leaving out here, and that certainly deserves a lot of credit because a lot of people are using it, is Wekinator, that is programmed by Rebecca Fiebring. She's a professor in London at Goldsmith University. If you are interested about it, I can, here, this is.
Maybe we could show that in our missing data now.
Yeah, maybe we can do that. So this is Wekinator. A lot of people are using this, so it certainly deserves credit for being an application that is used for machine learning in MaxMSP. But since this one runs outside of MaxMSP and you establish a connection with like UDP send and receive, like we showed you with the brain interface and the watch the other day. So this sort of stayed external, and for now the focus was to really to look at things which are available as MaxMSP objects. Yeah, so I will be looking at different objects that, as I said, are part of this ML star bunch of objects. You can find it, maybe I can show you this. If you open your MaxMSP and you, there's this so-called package manager. What that is different groups of objects which are released by different researchers. You can find, for example, objects released by SynMat in Berkeley. A lot of different things which people are releasing as objects in MaxMSP. I think we showed everyone also how downloading objects and putting them into the externals folder works, I believe. Did we? The other day?
For RTC mix.
Yeah. Because so all these things you also find on GitHub, and you can just like download them and put them into, let me show you. So if you go to your documents, you will find MaxMSP, and then you can add those to the library. or to, this is where those packages are added when you download them. Either one actually is recognized by Max. So this is just one way of getting these objects. The other possibility is, as I say, to download them via GitHub. And so what we are looking at today is called ML star. And I should say that all those objects that you find for Max MSP at the moment, they are certainly very much, as the whole like software, geared towards real-time applications. So all those applications that really require heavy computing and that might take a long time, like rendering a matrix in TensorFlow and stuff, you won't find in Max MSP. You can do those things by like externally creating matrices in TensorFlow and importing them as JavaScript objects. What we wanted to show you 2 weeks in the future, Google Magenta, they are working this way. But so these things that we are looking at now are really working in Max, and they are, as I said, they're very much real-time oriented. Yeah, so let's just get started. I will show you some different kinds of applications, which actually, so if you open this, you can see these different kinds of objects, which you can just click your way through it and play around with it. And you can get an overview of, like, let's say, a start of possibilities. And we will start with the Markov chain. So that maybe, yeah, you could say, yeah, very commonly used sort of application, Markov chains. I guess everyone here has heard about Markov chains before. Yes. I mean, since so many people are also.
It's basically, it's a probability dependencies where you have something here and you have a certain probability of either doing this next or this next, okay? And then depending on that, then you do the next thing. And then from there, you have a certain probability of doing this next or that next, you know? So it's basically just following these different link groups on probability.
Yeah, and it's, I think actually now, if you look at this, actually it sort of works kind of similar to what you just showed, right? In that you have an input, which can be anything. Here in this case, it's these numbers, which we put this in as a data set. Now, this is actually a much smaller data set, obviously, than what you had. I mean, I could also now have iterate these 5,000 times, but it also works with a smaller amount of data. And the idea with these objects is always to say there's an input, there is a learning, there's a mapping, and then there's a correspondence to either an external output or an internal processing. So I put this data in, I have this built, and then I can actually have this data put out. And what happens here is now that it's actually used with this, this make node object to create simple MIDI outputs. Wonderful. This here,
artificial intelligence.
I think it's very relevant to see to be able to change the order. So this means like how many states back into the past does the output in the future refer? And of course, the longer it gets, the more consistent the results get. I will show you this with text generation. So now this is fun. This is actually something that well, a little part of something that I used in a project some time ago. And so what we have here is text, which is actually the beginning of Ludwig Wittgenstein's Tractatus Logico-Philosophicus. And I can put in this data, and then actually what happens here when I put in this data, so this object transfers the ASCII keys into integers. So you need to convert it into integers. and it all runs here into the Markov chain. And now it's very important to see that what we did here is to say every time there is a full stop, the process needs to stop. Otherwise, the sentences like become independently get a length that is indefinite. So I'm using this like metronome object to deliver a bang to the Markov object to then output a number. I store these numbers here. And then once, so 46 is the full stop. Once the full stop comes out, it lets the list go through. Otherwise, you just get a bunch of vocals and let's say like just individual letters, but no actual words. So the question, of course, with this process is like, how do I make this spit out a word or a sentence rather than only just individual letters? Okay, so let's do this again. We can put in the data here, and then we click build. What happens if we click build is that it first defines the order, which I said showed you before. So it refers back for 6 states back into the past.
That's basically the average word length in a sense.
No, it's certainly like empirically speaking increases the consistency. Maybe we can try this out and do order 1, and then I think it's very visible here as opposed to like random major keys where you wouldn't necessarily know what is consistency in the way that you do with language. Okay, so let's do this, and I think now we should be ready. Yeah, very good. And well, and it's actually sort of, I guess that's why we chose things like this. It's quite interesting to see what sort of comes out and how differently like texts are read. And to make this even more fun, I can actually engage the audio input. Yeah. And so now every time the sound comes over a certain threshold, it will trigger a bang. So this. Okay, at this point you gotta be reading very fast. No.
I know that guy.
Okay, let's stop the audio input. Now, of course, you can also add actual text. So I can write text into here. And then, oh, I need a full stop. Otherwise, I think we'll never stop.
Here, I know that guy too.
I don't know. No, it doesn't work. Very interesting. Try this one again.
Oh,
Oh, yeah.
Oh, yeah.
Yeah, it's in there.
Yeah.
Yeah, so maybe that was actually too small. Interesting.
Yeah. Or maybe it's not getting cleared completely.
Yeah.
Because it was funny, it was embedded with the other stuff.
Yeah. Okay. So let's see. Actually, you can use those Markov chains also. There's like hidden Markov chains, and do a couple of other things with it. I mean, this is sort of course, Markov chains have been used in generative music for a very long time. So I'm just going to skip through this
Xenakis was a big Markov.
very quickly. So let's see. So I have here's this object is called MLHMM. So for the hidden Markov chain. And I actually have different kinds of data input. So first, what I'm going to do here is to feed actually 3 different keys, and it can actually distinguish different keys. You will see it here. See the number change here for the different sort of sets. So what's happening here is that you have those inputs and they get a different state. So the interesting thing here is that it can distinguish between different states, and we can actually map tonalities like this. So let's put in data, build the model, train the model, and now. Oh. And now you can see a number here. This is the state that is changing, which now actually is the different kinds of scales that I put in, which it's changing between. Okay. So far, let's do something else. This one here is using chords. No, this one is also doing scales. So this is 7 different major scales. You see here now it has 7 different states. And so forth and so forth.
Nicola, let me
Yeah.
ask you some basic questions. What is it that you're sending it to train it?
Right now here, let's take this example. Just sending in these different numbers.
And those are scales that you kind of predetermined.
Yes, exactly. And this is just like MIDI pitches, right? As MIDI pitches.
Yeah.
But since those are sort of like, let's say, starting at C-2, so at 0, I need the +60 here. Otherwise, it sounds like you heard in the beginning. Now I'm going to show you what happens. Wait here, so I can also like play this by myself. Wonderful. Let's see. And because this one here, of course, it doesn't start at 0 the way that I configured it. So I need to not have it at 60. Okay,
so the Markov process is that every time it lands on one of those notes, then it has a certain probability of going to the adjacent notes, or?
Yeah.
I got it.
So that series of numbers that we call scales, are those each numbers of each different pitches?
Yeah, exactly. Every number. So this is just MIDI. Every number is a different pitch, and you start at 0.
Scale, a series of notes. So they're kind of like melodies.
Right.
Yeah,
So
yeah.
like a C major scale, the numbers would be 0, 2, 4, 5, 7, 9, 11,
Yeah.
12.
Yeah. Okay.
So they're basically just counting semitones.
Yeah. So let me show you where this goes. So you can also load external MIDI data, of course, and you use the sequence objects to load it in. Right. And this was very fast now. Of course, we don't want to sit here forever. So when you click start, and this number actually defines the speed. So 1 would be the original speed, and this is now 65,000 times faster. Okay. So now, of course, the training takes a while because now we have much more data than we had
So
before.
there's a whole piece then.
Exactly. Yeah.
What's the piece?
What did I use?
Sorry.
Bug 850. Well, I have some few that I used. Okay, let's play it. And now what it actually does here is that the different states are not predefined, but it sort of guesses the states, which is where the hidden object comes into the hidden Markov chain. And you can see it guessing the state, and basically every node now is a different state. And here I'm defining that 32 is the maximum number of states that it can use to like map the material. Okay, so just like one last example of Markov chains, and so it is something like this. And again, same thing, we load the MIDI data in. A little bit slower. Okay. And now we, so the idea with this one here is to say, okay, we can link different Markov chains to also, for example, describe tempo and describe different chords to become a more, to get a more flexible structure. So the idea is essentially we are linking up different, so if you look at this here, you see I'm using 5 different Markov chains here in order to get the pitches, velocity, chords, onsets, and note lengths. Okay, let's play. Already becomes way more interesting.
Some backwards,
Yeah.
It's just twisted.
Yes, very much. And it's actually, so now it sort of stays quite fast. Let me see. I mean, now this is the manual note length. Let's see. Earlier it was going to a place where it's not just fast the whole time. So maybe, I don't know, I have to change the audience. Anyways, but so I guess you get the idea that by linking up those Markov chains to different elements of the data that you're providing. So for example, the one for the onsets here works by getting the samples and then translating the samples into the milliseconds. So you find different ways of how to actually reference the data which is provided. And you find different like dimensions of how to describe this. Yeah, I'm just like jumping through this a little bit because I mean, it's going to be uploaded later anyway, so you can just have a look at it, but at least we get through everything. Okay, this one here. So now I'm showing you a couple of things which will eventually come together. This is an adaptive resonance theory neural network. I should ask this. Does everyone know the difference between supervised, unsupervised, and
I forgot to mention that.
Reinforcement learning? I guess everyone in computer science knows about this.
I've never heard those terms.
Okay.
Basically, what I showed you guys, that was supervised learning because I was giving it a target that it was trying to like actually make the data values go to.
Mm-hmm.
Unsupervised, you don't, and it kind of figures out its own target in a way, and kind of like that basically it's extracting features from the data automatically at that point. So yeah, there's it in a nutshell, I think.
And yeah, and so this one here works in an unsupervised fashion, and I think there's definitely, well, I don't know. I think it's quite interesting to work with unsupervised learning in like systems which attempt to have a certain fluidity without necessarily a well-defined goal. Like, let's say if you try to be able to like tell the faces of millions of people apart, have quite a different aim from like programming computer systems, which are able to improvise, where maybe you are looking for emergent orders rather than a predefined result. And I think that's where I get quite interested in unsupervised methods. Okay, so what this enables us to do, and now I can put in here 2 different values, which are between 1 and 0. And it will map those values here. You will see later how this comes together. Okay, I can create this here. And
Now that's just the straightforward mapping, right? It's not doing anything.
well, no, it's not a straightforward
Well, it's
mapping.
upside
That's
down, it looks like,
that's the okay. We can actually change the threshold and also change the learning rate of those here.
Okay. Oh, I see. So it's learning from what
Choices.
you're putting into it.
Yeah, exactly. So that's the point.
What is the heat map kind of?
Huh?
It goes from green to red. What is the difference?
Well, honestly, I'm not so certain if the colors have any meaning other than a design choice. Because this part is really just the color plotting, and I don't think it has any like.
No, it was straightforward. Yeah.
Okay, or I could use a microphone input. And now what I'm doing is I use this object fiddle. It's also written originally by Miller Puckett, who also developed Msp and Pure Data. And it's one of those objects which are very like regularly used for pitch tracking. So here just on this output, it gives me pitch and amplitude, and what I'm doing here is just to unpack it and to use those 2 values, so velocity and pitch. And I can actually, now you see I'm speaking, and the training process still goes on. So I can also use audio input or whatever sort of input to do this. It's interesting one about this one here is that it generally works with 2 dimensions. The next one that I'm showing you is working with more dimensions. So here you are basically putting in 2 values at a time, and it will perform a certain adaptation. We will see how this comes together.
So basically, the different colors then are kind of like a depiction of the features that it has abstracted.
Well, definitely what you can see here, let me reset this.
Okay.
And if you see here, definitely the y-axis is related to pitch. But of course, whatever that is also very much depends on the kind of data that you put in. So if I would be using a different tool, which doesn't, for example, track pitch, but for example, tracks noisiness, then I get a whole other result. So I think that's very important to see that really the defining the input is so relevant for the artistic use. And then also, for example, now if I would be using this in a piece of some sort, I have to make a decision about what is it relevant for the machine to get as data. So like, let's say I would be working with a microphone input. What does it need to listen to? And so basically the decision about what it needs to listen to is taken before the machine learning even happens. And I can actually also use it. Let's see.
It's
Yeah.
ML machine learning.
Can you say it again?
Is ML machine learning?
Yes.
Yes, that's what it stands for. And so now with predict, I can stop the learning process, and it actually correlates the input. So that's also partly of what you, the sort of filter thing that you showed before. So that works very similar now. Just that I don't have a defined data set in the way that you had it.
Because it's made up its own.
Yeah, exactly.
Interesting.
Okay. Let's go on. So this is a self-organizing map. And the self-organizing map is very much used for dimension reduction. So the idea is basically how can I get data in, which has basically, I don't know if it's correct to say indefinite dimensions, but certainly much more. And to break down this data to a two-dimensional space that then still sustains the structure of the data in a two-dimensional space, and to be able to export it from there again or to do whatever with it. But really the idea here is to do a dimension reduction. So let me show you what happens here. I'm generating different colors. Now this is 8 different kind of colors, and I can map them into here. And I can go across those like this, and then I can get a mixture of these colors. Now this doesn't look so spectacular at first. But it is sort of interesting when you think about it in terms of synthesis, for example. And if you think about like developing mixed sort of parameters for synthesis and so forth, I will show that to you later. So let's just use some random values to actually feed this kind of process. And it moves a little faster.
Oh, cool.
And so the idea with like self-organizing maps is to have like, let's say, represent the structure of the multidimensional data on a two-dimensional space, which like, let's say, has a correlation to the multidimensional data. So that means the data that is mapped here is not mapped here for no reason in the way that it is ordered, but the idea is really to have it's a Euclidean relationship that is basically dimension reduced. So I will show you.
It's a way of trying to smooth out the data so that it kind of fits together nicely.
Yeah. Yeah, so let's do this. Yeah. So you actually find this one pretty much also if you go through the Max MSP package. There's just one send object which has a wrong name, which is why it doesn't work. You need to change the name of the send object, or you can just download it from the CMC server then after the class and implement it into your own package. Then it actually works. So what we are doing here now is to have an FFT analysis, 48 bands of the incoming audio stream. Once I turn on the audio and turn this one down. And you see the 48 band analysis up here. And now this is fed into that process here. And now we have data, which basically has 48 dimensions, and we're able to reduce it to 2 dimensions here. So, so we can just like keep it running for a while. And now I can click into here and I get an output that actually comes from here. So I get the XY data of where I am clicking with my mouse. And I put this in as a comparison value. And then it will actually, so that's where I'm saying we have 48 dimensions of data. This is broken down to 2, and I give the input about these 2 dimensions to the process, and then I get 48 dimensions out again at the end. So this is what you see here. And now, of course, we can use this to synthesize. And the idea here, of course, is that you can, transform this. I mean, it could be many different things. This sound might not be the nicest, but I hope the idea is clear that you have a spectral analysis that is performed, you break it down, and then you're pretty much able to do anything with it, and it works like a sort of memory for the spectral analysis, which organizes these. So if you look, I'm clicking around here, and there is a proximity between this data. Here, you see? Yeah. So this, and that's interesting because it's able to sort of break down the spectral components over time, but taking out the temporal linearity of this data. And if I click somewhere else, you see I get a very different structure. So the idea here is really that the similarity of the data is sort of like consistent, independent of time, and you can really use different positions of outputs.
You guys see how that's working, right? I mean, it's like each little square is almost like a snapshot of one of the FFTs that we're taking. And what the map is doing is trying to organize it so that all these different snapshots are related to each other by their proximity.
Yeah.
So like as you move from say there to there, you'll see that one hump kind of go up like that.
Yeah. Okay, so that's a fun little exercise. You can actually, sorry, this is sort of a step back, but you can use the same idea. Now we get back to the fun MIDI data, to organize MIDI data. And you're dumping this data here now, and you can see again the same thing, that local proximity is also proximity in the output, and that's again now the sort of extended dimension version again. So we have all these pitches coming in, they're broken down to 2 dimensions and then like unfolded again, you could say. And of course, we can use this also to now use a random process. And basically, here you see this. This is basically also just a table for like a chance operation. So basically, the higher, so this is the different kind of pitches. And the higher this value here, the higher the proximity, the higher the likeliness for this pitch to sound. So that's what we can do here. And now these 2 things, so the art and sum objects, so ML art and ML sum, we can bring those together. maybe this is taking too long if I go into this. So let's go here directly. So the idea here is that you can also use this to map this out to a synthesis process and actually have some machine learning performed on the kind of gesture that I perform for like drawing here. So let's see. Okay. What it does now is to analyze the sort of shape that I'm doing. So this is where we will look into this more next week with Mubu, because I think the capacities that it has are quite advanced. But here, this art object is used under the hood to over here. Art object is used under the hood to identify the kind of movement. So this is where this idea of resonance and being able to determine a certain state and building it up over time sort of comes in. And you can see that, okay, let me clear this, different kind of gesture. Give me different parameters that's down there. So this is now 9 different parameters. Okay, and now we can actually link this whole thing up again. So here we have the ML sum object that is doing a spectral analysis on the sound in the room, and I can actually link this up. And yeah. So there's just one big object that doesn't initialize when I started the program. Here, okay. And now you can see I can click here. So this is as a kind of memory again. Put in an XY value. And you see this is the synthesis parameters down here. But this is the result of a 9-channel FFT analysis of the computer microphone input. Now.
So it's basically everything in the room so far.
Yeah. But the idea here is really to bring this ML sum object. You see it over here, which I showed you before, and ML art object together to say to bring movement and sound or whatever together. But it is actually interesting to team up. Sorry, I'm sort of running through this a little bit.
Question for you about the gestures. So when you define a gesture there, that gesture is then being mapped across the alpha GML sum thing.
Can you say it?
Sorry. Yeah. When you make a gesture, is
Yeah.
that gesture then being mapped across the output of the ML?
No. So the idea here is to basically have the synthesis process, which is happening in here with these grain parameters being derived either from the ML art and MLP object from this drawing to go into the synthesis, or to have this come from here, which now comes out of the, here I'm using this set as a centroid object, so that determines the pitch center, also works for noisy signals, and then maps those in here. Okay. And now the interesting thing is also that you can do this actually without me interfering. So this is now giving us outputs from here, and it actually becomes feedback process.
Ah. Hey. Whoa.
So now what happens is that current audio input determines the basically XY value, which is read out of here. But that is, of course, not the current sound, but the past sound that is stored in here. Right? And that then is used as an input over here. Maybe actually, if I invert these values, it's a little bit more glorious. Let's see.
Wow.
Or you could actually also use the live input. That maybe. Well, okay. I mean, this would be a little bit of figuring out, but I guess you get the idea.
If you don't see Nicola later.
Yeah.
Okay, so I have one more thing that I wanted to show you, which actually works with video. Maybe I can show you the video thing directly. So now this is also sort of fun. This one here actually works with a JIT matrix. And this is JIT ML LZW. And what it does is to analyze the complexity of the video image, or you could also say the change over time. And basically, the more consistent the video image is, the more, like, let's say, it will tell us that nothing is happening, so there's no change. So it basically gives us an indicator for change. I will show you this here. So I'm using what I'm doing now. So the sound that you're hearing is this value here mapped to a sawtooth and a square wave. And what we are measuring here is basically the activity. So let's see what happens over time. You see how this one here goes down over time. And that is basically because nothing is, so the fields is not what the video is. But this. So now this is like relatively active here. And of course, I cannot keep this. We will see the same process because nothing much is happening. Doesn't change. Now that it is. Back to where it was. So it still has the model of it. See now, see, oh, different. Now I can just do nothing, and again, the model will become more adequate for what it is. Okay. Right. So you see, I put in this string of numbers, and when I repeat putting these numbers in, let me move this. Right. Okay. Okay. Watch here. So this is the numbers I just put in. And what happens if I keep on repeating this? That actually the output shrinks over time.
Huh.
And it actually confines to one specific number that actually is not part of the data set. So the idea here is also to compress data to a specific middle point. We will also be looking at fuzzy C clustering. I could still show you that, but it's so the Mubu and this one both do fuzzy C clustering and also K nearest neighbor. So, but this is basically three different functions which you all use in order to somehow work with the idea of proximity in the data set or distance. But you can see it is sort of going down. And this is exactly what we were seeing in the video as well. Just that this, well, doesn't have a sound. But yeah, I guess, well, that's sort of what I wanted to show you for today. Do you have questions about this stuff? I'm sorry, I went through this like very quickly, but I wanted to make sure that I get to the end of it. And now we still have 10 minutes, so we can go back to things if you want to ask something.
I think the thing to take away from this is that these are very powerful ways of being able to combine different data streams, you know, like if you're looking at weather data or something, you know, or cancer data, you know, this might be a way of sort of coalescing. It's interesting because that's the kind of thing that Ben was showing in his presentation, where he had some of the notes that would like extend out. it was a way of kind of clustering the data and, getting kind of more information out of it in terms of your perception of the data stream. I would say that, take away from this, these different techniques, and if there's one that you think might be applicable to something that you're interested in, write to Nicola. Yeah.
Yeah,
and he's used this quite a bit, obviously, and he's pretty familiar with how it works and how you get the information you need out of it.
yeah. And I mean, definitely, I mean, we will load all of those patches up, and if you look through it and you feel like, oh, this is sort of unclear, don't hesitate to get in touch, and I can help you get through it. As I said, it has so many layers, also the synthesis process and stuff. If I went through everything one by one, we would not have made it to the end ever with this. So that's why I sort of didn't do that. But if you want to understand those things in depth, please. Yeah.
I like that. We would not have made it to the end ever. Yeah, I mean, there's some pretty dense math programming there too, but a lot of that is to sort of do the whole package. Whereas you might need just a single component stripped out of it, to kind of look at your data or do something. Yeah, this is powerful stuff. Yeah, like I said, I'm glad I asked you to do it because I don't know really what's going on with all of it. So, yeah, it's interesting. The stuff that you're showing, like the feature maps, that was the Cohonen feature map. I know about those because they're ancient. Lempel-ziv coding. That was the original thing used in the Unix utility called car, which was the first kind of archiving program. This is like, when you use Apple compression, when I make the compressed file, using Lempel-ziv coding. And in fact, car stands for tape archiving because you would archive actually onto a magnetic tape because that was your storage medium back in 1985. Yeah. Did you? Yeah. Oh, the old TRS-80s and stuff like that. Yeah. Amazing stuff. Yeah. Wow. So this is and we'll see more interesting things. And what'll be fun is, especially when we get Pierre and Federico in here. These are the guys who've actually developed some of this stuff. Yeah, it's been interesting. Yeah, I think maybe in that missing, we can't talk about the Wekinator. I can talk about that.
Yeah, I guess we can both do something about it. Yeah. But I think Wekinator would be good there because it definitely. I mean, so Wekinator, I think is probably one of the most used like machine learning applications in the Max community. Absolutely.
Yeah. It's basically the gesture thing that he showed where he could draw across this. Wekinator is like a superset of that, and you can basically take any sort of thing that moves in time, and it will learn that thing that moves in time, and then you can attach different things to it. Like as this goes this way, do this. Here's a really remarkable demonstration where it was she was actually at Princeton at the time she developed it, and she had an installation set up where she had a pet snake, and she put it in this sort of box, and she had a camera down. And Wekinator learned the different configurations of the snake. So as the snake would go and move around, it would like change the audio output. And it was really cool. Rebecca was a lot of fun. Yeah. So that's kind of cool.
But is that how she developed Wekinator for this piece?
No, that was her research stuff.
Okay.
Yeah, she did. The piece was more a demo of what she was doing.
Okay.
She did this for the piece. Question?
Oh, yeah, I got one question about how I think every generation algorithm you showed to us are unsupervised, including the Markov Chains.
Yeah.
Okay. I don't think there are any supervised in case of using.
Not really. Well, the part of it is also if you're doing something in real time, it's inherently unsupervised because you don't, unless the supervised example that I've seen are things like a lot of pitch trackers, that they use in like piano tuners systems. Those are actually neural nets now, but they've been pre-trained. So basically the network works very, very quickly. but that was supervised because it would say, when you see this, that's a C.
Yeah,
Yeah.
Mubu has some simple supervised learning possibilities, actually.
Right.
And about the pieces you showed us, I'm wondering if the state in the Markov chain is one node or a sentence or several sentences in the piece.
It works number by number,
It's a node.
but of
Yeah.
course that's where the order comes in, because then you can.
Because it's meaty, right?
Yeah,
It
exactly.
can be, it can be.
It can be anything,
It can be
really.
anything. Yeah, Markov chain is
you-
just an abstract concept, you know.
But if you put in the audio, it should be like part of the audio, it shouldn't be like just one node.
Well, I guess that's what I was trying to show with the. Let me open this again.
Oh, you're opening it. Basically, a node is just a state, and then you've got a probability of going to other states. What you define as that state is up to you. It could be a single MIDI pitch number. It could be a collection of MIDI pitch numbers representing a chord, because you could have a chord that moves from one thing to the other.
Well,
So everything is included in that.
yeah, I mean, so with these ML star things, all of them work with integers. That's why, for example, here, what I did was to transform it down into 2 integers, because it's a 2-dimensional thing. So that's why I sort of transform down the sound into pitch and velocity. With the Markov chains, that's another example where it's clear you put in integers. That's why when I put in the text here in the beginning, exactly. Let me show this to you. So maybe that's more impressive. So here's the text, and this is what the integers look like that I need to enlarge this a little bit. That I feed into this. It doesn't really capture everything, but you know, I'm just feeding in the integers.
So like 97 was ASCII for capital T.
Yeah.
Oh,
So it's just turning those guys into ASCII numbers. Yeah.
Yeah, and so with these here, definitely then the question is how, if I want to work with sound, how do I transform sound into integers in a meaningful way? That's what I when I said you have to decide whether, for example, pitch tracking is relevant or other things are relevant. So that's really a decision about like the transformation of the data that is already a compositional decision. With Mubu, we can actually work directly with sound, for example. But I think with all of those things, it's always, translation and interpretation between different representational forms is very relevant to the artistic activity in doing this. Because in the end, deciding that, for example, I want to track pitch, want to track a sound as pitch and not as something else, that's already a compositional decision that might not be relevant for every kind of music, or for every kind of case. I could also be just tracking the onsets, for example, and just use the onsets and only track the onsets or whatever. There's so many different options of how I can map out the infinitely complex input of an audio signal into its representation.
And that's up to you. That's at the very beginning when I said the coding of your input data is a big thing to do, because you're going to automatically predefine a whole bunch of stuff depending on what you choose.
so this is part of the hyperparameter.
Yeah. And I still want to say that, let me turn on maybe I don't need the screen sharing for this, but so Ben Smith also has a page on academia and has written a bunch of papers also about these objects. So as with, I think, everyone in the Max community, or just as everywhere else in the computer science community, everyone who programs software like this will also write about it. So that's certainly also helps
links up on the class.
going to the page, and also to have the possibility to read more about this if you want to have a more in-depth understanding of the code.
We'll create an archive of the the versions of these things that Nicola has done, so you wouldn't have to go through the package manager. You can just basically abstract them from our.
Yeah.
And that way you don't have to search for the object that was misspelled.
Yeah, exactly.
I'm glad you found that.
Yeah. I was looking for the mistake for a while. I never understood why it was working.
Hey, gang. Well, we're about at the end. I'm going to turn off the recording. I have 2 announcements to make.